Welcome to Lab 4 and Lab 5. In Lab 4, we are looking at pandas. So this is a continuation of what we started in Lab 3, which was NumPy. So NumPy lays a foundation of advanced data structures in Python, and the pandas is built on top of that. So understanding how to operate our data, how to work with the NumPy is very important on your journey in data science and machine learning. And it will help you understand the other advanced data structures like pandas. So data structures that are found in pandas in our case are two. We have series and data frame that we're going to look at. So pandas is like a library, as we also saw that NumPy was a library, and inside that particular library was a data structure which was actually ND array. So we are able to create ND arrays, but sometimes instead of saying ND array data structures, we can just say maybe NumPy data structures. But when we say so, we are actually referring to ND array. So the same here, when we are saying pandas data structure, we are not really, we don't really have like a pandas data structure, but pandas library or package has got data structures. In this case, we have a series data structure and a data frame. But we can sometimes just say pandas data structure. When we say so, we are referring to series or data frame, and commonly to data frame, because data frame is more commonly used. So when we say data, maybe pandas data structure, sometimes we can interchangeably use that instead of data frame. So these are two data structures that we're going to look at, and for us to be able to use them, we must import necessary libraries. So in this lab, I have indicated that you can import pandas as well as NumPy. So in this case, NumPy is not really mandatory. You can have pandas and do so much with pandas without NumPy, but we've included NumPy in our case because down there is a section somewhere where we'll be creating some data structures from pandas, in our case data frame, and that kind of data structure will be created from NumPy array. So that's why we are importing it here, but it's not always that they'll come together, although in most cases you may have pandas and NumPy imported together. So let's start with the first data frame. But before we do so, let's make sure that we are connected. In my case, I'm connected, and let me just run this cell. You can be following me as well, running your cells, checking how they are behaving. So we are starting with the series data structure. So you can think of a series data structure as something equivalent to one-dimensional array from NumPy. So think of that as one-dimensional array, or think of that as maybe one-dimensional list. So this one is a structure or data structure available in pandas, but it differs from one-dimensional array like NumPy in two main ways. One, we see that in this statement we are saying you can name the indices of the series. You should know that if you have an array, indices start from 0. If you have an array of NumPy, so we are going to have indices from 0, 1, etc. And we cannot rename them. We cannot change them. But here in series, you can change them. It's like you have an array, but maybe you can choose to say, instead of starting first element to be on 0 index, you can have it on 1. So you have renamed it. Or you can even give it a text instead of a number. So maybe the first one can be first person or first student, and the second element can be second student, or first grade, second grade. So you can use such things, maybe a string, or even just numbers that are starting from somewhere else, not necessarily from 0, as is the case with NumPy. And another difference is where in NumPy we store data of the same data type, with the series you can have a mixture. You can have numbers as well as the other data types. So to create a series, you use a function, or you use something like this one, which is the pd.series. So you use the pd.series, and that one has got two things. Of course, the most important one is the first one, which is data. You provide it with data that you want to use to create that particular series. But you can also provide it with the index. So the index is what you use to rename your indices. If you don't put index, then it will create a series with a default indexing, which starts from 0, as the case with NumPy. But you can also choose to give it your own indices. So you do so by putting something under index. In both ways, you can provide data to it in a form of an array or a list. So let's see an example here. We are having a small example creating that particular series, and we have only provided one part, this one. We only have one thing instead of having two things, because things are separated by comma, but here we have only one thing. We are only providing a list. So what we are providing there, it's a data. We are creating a series with this data. We haven't provided the second one. So in this case, it's going to create a list, a series using default indices. If we run it and print it out here, what we've created, we see that this is our data, and this is a section that is showing the indices, and our indices are starting from 0 up to 4. So similar to NumPy, because we didn't specify indices in this case. So this is how data in a series is displayed, or in Pandas is displayed. For a list or for a series, we can have it shown as shown here. It's more or less like we have two columns, but it's not two columns. The second column in this case, which is deemed to be as a second column, is actual data, and the first part here is the indices. So if we remember from NumPy, when we displayed it, it just showed an array, maybe 10, 20, etc., just like an array in a box or something like that. It was not showing the indices, but in this case, using Pandas, it shows you the indices and the data. So the first column there is showing indices, but the actual data is in the second column. So this is a series. Now that we've created that, we can now demonstrate how we can create a series, but now with the indices renamed. Maybe before we go there, this, instead of writing it directly here, because it's just data, it's just a list, you can even have it somewhere before. Maybe you can put it somewhere like this. You can create your list there, and then you can feed it here to create your series. So let's try to run this one again. So it will run. So it's up to you which one you are comfortable with. You can have it directly there, or you can keep it in a variable and pass the variable in pd.series. So the same applies here. But here now we see that we are creating our series using two lists. So the first list is for the data. This is our data. And the second list is for the indices. So we've renamed our indices. And if we run it, we can see now that our first number, which is 10, will be on position 1 or on index 1, and it went on index 2. So we've renamed them. Instead of using the numeric values which start from 0, we are now having strings that we have given ourselves. So that's the most important thing. We are not able to do that in NumPy, but we are able to do this in pandas. So as before, these ones you can have them before, you can have them somewhere here. Maybe this can be data, and this we can have this one. It's up to you, whatever we can have. Maybe let's see. Okay, maybe we can have this one as indexes. So whichever variable. Okay, so we can put it there and just write like this to make it maybe more legible. So you can separate them like that. And here it shows that the first one is an array of data and another one is an array of corresponding indices for that data. So if we run this one, we are going probably to get the same result. So here we are trying to show that, of course, apart from this, we saw, I think, from even other things, like maybe in the previous lab when we were looking at NumPy, that it's not always that we use print to display things in notebook. So we can just maybe write the variable and it will be able to print results from there. So let's try to print what is in X without using a print statement by just writing X like this. And in Python pandas would create, or pandas creates a very good, beautiful output from there. So this is more beautiful as compared to the one that was displayed using print. So in most cases, when we're using pandas, we do not really use the print statement. We just display the result because it brings or gives us a very beautiful output. Something that looks more interactive, or maybe something that looks more beautiful as a table. So from here we see that if we are to look at this, we have this column which is showing indices, and those indices are shown in bold, and these are values, and these values, if you can consider this one to be a table, then these values are on another index which is 0. So it's on index 0, and this one is also bold. So it's like it's on column 0. So this one has got only one column, which is column 0, but many rows, which are starting from 1, 2, 3 up to 5. So 5 rows and 1 column. That's where we have our data. So similar to NumPy, we have a number of attributes that we can use to describe our NumPy, our series. Like in this case, we may want to know the size, we may want to know the shape and the dimension. So a series is one dimension, as we said, so it's a rank of 1. That's why it's showing 1 under x.ndim. It's one dimension. And the shape, because it's one dimension, so it will show us something like that, like this one, 5 comma. It has no second dimension, so it's only 5. And 5 comma, it means because it's one dimension, it means there are 5 elements in it. So size shows the number of elements that are available in our data structure, in this case in our series. And we also have other attributes like for index and values. So the index, let's just run it and discuss what they mean. So index will show us the indices, or retrieve the indices. So sometimes you may be interested in the indices and not the data. Then you can use the index to get something like an array or an iteratable of indices, and you can use that. And here we also have another one, dot values, if you're interested in values. For example, let's assume we are just interested in indices, and maybe we wanted to use them for something else. Maybe for now we just wanted to display them. So I can say maybe index in in what? That is x in x dot index. So something like this one, I'm taking one index at a time from there and printing it out. If I do something like this, it will be able to just give me the indices. So I can use them in whatever form or in whatever operation that I want. It will be just data. So you can be interested in the indices, or you can be interested in the values themselves. If you want to go through values, then it will be in values. So each variable is taking a value at a time, and now you are going to have values. So you use those attributes .index or .values to get either index or values from our data. Now that we've created a series, we should know how to access them. Remember, from NumPy, we are able to access them using indices. You specify an index in a bracket, like a square bracket. So the same applies to accessing elements in a series. You use a square bracket to access them. So let's see how this is actually done. We are first of all creating our series as before, and we are trying to print the one which is on index 0. So because we are coming from NumPy, we are aware of this one, of this particular syntax, that if you wanted to display the first one, we just specify the index which is 0, like in this case, and it will give us what is on that position. Of course, this one is duplicated, but it's still supported. But we avoid accessing elements in Pandas in this manner. Instead, Pandas introduced something else that would help us access the elements, and we call them a loc for location. So instead of just writing something like x0, we can have something like .iloc if you want to use the integer location, or just loc if you want to use the named locations or the named indices that we've created here. So if I run this one and maybe try to go through the output together, we can see that we are able to print out this x0. x0 is our first element and is able to print 10. So we can use syntax similar to NumPy. We are able to get that. Or we can use a syntax which is more specific to Pandas, which we use iloc, x.iloc, and you specify the index. In this case, 0. It's also giving us 10. Or you can use the .log for location if you want to use the named indices. So if you just say iloc, then you need to use the default indices. But if you say log, then you can now use these named indices. So if you put 0, that is index for the first item. So if you put 1 here, so we've used that one here, and it's also giving us 3. In other words, we are saying there are 3 ways how you can access the Pandas data. 3 ways to access them using indices. You can use index style similar to NumPy, or index style that uses iloc, or that uses a loc attribute. So we can see here that it's similar to NumPy in many ways. We are able to use even negative indices. In this case, we are saying x.iloc -2. It means the last but 1. We are counting from the last element. In that case, we are starting from 5, then 4 element which is there, which is 40. So it's supposed to give us something like 40, or we are trying to modify where there was 40 and we are putting 100. And we can also modify using the named indices. In this case, we are deferring to the one which is index number 5, the last item, and changing it to 200. And finally, we are displaying it, and we can see that indeed that element which was 40 is changed to 100, and that one which was 50 has changed it to 200. So we are able to use negative indices, positive indices, as well as named indices in Pandas. And here we are showing you to say sometimes you may be interested in multiple items. And if you are interested in multiple items, you can provide those indices as a list. So in this case, we have our outer bracket, and we are not only looking for data which is on position 0, but data which is on position 0 and position 2. So we provide those positions as a list. So if you want 0, 2 and something else, we can also specify that something else. But in this case, let's just look at that which is on position 0 and position 2. So position 0, that should be our very first item, 1. And on position 2, we are jumping in position 1. Then that will give us that which is on position 3. So you can use that. And if you want even to include it on position 4, for example, you just put comma, then position 4. So it's a list of indices. You can use that. Similarly, you can also use .log. It's a list, and it can be a list of named indices in this case, maybe 1 and 3 in this case, and it's able to give us similar results. So it will give us that which is on index 0, index 1, and that which is on index 3 in this case. So you provide it as a list of indices. Yes.
So you're putting 2 positions, and you're putting 2 brackets, the square brackets. So if you put another digit, you add a bracket, yeah?
Like here we have 0 and 2. So
can you add 3?
Yes. So this one is a list of it's a list of, I can take it out and put it somewhere here. It's just a list of indices. So I can just call it indices is equal to this one. So this is a list of indices, and instead here I can write indices. So it can be a variable. So it's a list that I'm putting inside here. So to avoid maybe having many square brackets cluttered here, you can separate them. So you are specifying the indices here. If you want 3, you just put 3 here. So there are 3 positions you are interested in. So in that case, if we run it, this one is going to have 0, 2, and 3. It will take that which is on first position, third position, and fourth position.
I'm saying,
yes,
you've put two square brackets.
Oh yes.
Two index. So if you add another index, so like it will be 3 indices. So you have to put also 3 brackets?
No. You just put it like this. If I'm to write it directly inside there, then it will just be like that. So it's a list inside that, like this one. There are 3 indices, but we've just put them in one array or one list. So it's this part which we are putting inside. So it can be anything else, like you can put 1 as well. So this one has got 4 indices, but they've been provided here as a list. So you are telling it to say, I want elements that are on position 0, 1, 2, and 3. But if you are just looking for a single number, then you just provide a position to say that which is on position 2. but because we want multiple indices, then those multiple indices must be provided as a list. So we are providing them as a list. Here we are also doing the same. A list of first and third. I don't know if that helps, Peter.
Yes.
Okay. Okay, so that's how you access elements of series. We may also want to delete elements in a series. How do we do the deletion? There's a function that we use, and this function is called drop. So drop is going to drop elements, but drop, as many other functions that we're going to see in Pandas, behave in two ways. They behave in what we call doing that operation in place, or doing that operation out of place. When we say it is doing that operation in place, like in this case, maybe deleting in place, it means the original data structure will be affected. And if we say it is doing its operation or deleting out of place, it means the original data structure will be kept intact, and instead the deleted data will be copied into something else. So let's see what we mean by that. In here, we are first of all trying to demonstrate out of place. It means the original ones will not be affected. So we've created two series here. The one which has default indexing system, and another one which we have specified the nameless indices. So we have X and Y. And to drop, you need to know the position of the element you want to drop. Like here, we are dropping that which is on position 0. So it's X1. So in X1, in here, we want to drop that which is on position 1, 0, 1. Indices start from 0, 0, 1. So we are dropping 20 here, but we are dropping out of place. That's why we are keeping the result. After dropping, the result should be kept in Y. So that will not affect X1. The dropped one will be kept in Y. So X1 should be intact in that case. So we are trying to show what is in Y. And here we're also dropping, but using named indices for the second one. And it's also out of place. And we're keeping it in Y. And we are trying to show what is in X1 after deletion. So we have X1 after deletion is 1, and X1 after deletion is okay, this one I wanted to say X2 after deletion is 1. So we want to see how they changed. And what about the original? Did the X1 change? Did X2 change? So we want to see those values. So if I run it, we see that X1 after deletion is having index 0 missing, was dropped, and the X2 after deletion has also index 1 missing, which was dropped. We dropped index 1 here, but those are variables that we kept in Y. But what about the original one, X1 and X2 as original values? But if we print the original values, we see that the full data is there. Despite that we deleted something, but the original variables are still keeping the original data. So if I come down here and try to print what is in X2 or maybe X1, if I just put X1 and run it, we see that X1 is still keeping all its data. It's not losing any data, but we dropped some data there. So what it means is, if I write something like this dot drop, and drop that which is on position index 2, maybe something like that, and I run it, it will show me that it has dropped it, but really the data in its original data structure x1, if I run it again, will be intact. So it is not deleting the original one, it is just deleting and keeping it as a copy. So that's what we mean by out of place. Sometimes we may not want to modify the original data structure, and that will make us to go for out of place deletion. It can be anything, maybe out of place deletion, out of place insertion, and other operations that we're going to see under series as well as under data frame. If you want it to modify the original one, then you use what we call in place. You don't just provide the position, but you also provide a second argument which is called in place, and you put it to true. If you put it to false, it will behave as before. It means it's out of place. But if you put it to true, it means you want the modifications you are making to be applied on the original. So it will change this structure. You are actually removing the origin. So in this case, when we run this program and print the values of x and y and x2, x1 and x2, we see that the values are gone even from the origin. So deleting in place will affect the original structure. And if I come down here, even as I did before, to say, okay, let me see what is in x1, going down, I'll still be having data which is having index 1 missing because that was deleted. So when we use in place equals true, it means we want the infix to apply to the data structure that we are making that operation on. So those are differences between in place and out of place. We're going to see this coming again and again. Most important one, for in place, you don't need to keep it in another variable because you are changing its original structure. But out of place, for you to use that down there or later, you have to keep it in another variable. So you're making changes and you're keeping it another variable because it's a copy. Then you can use that copy down there if you want to. So that's the main difference between the two. That said, we can now go to the part of element-wise operations in series. We saw something similar to this one, and we're calling it broadcasting in NumPy. We're saying NumPy is more powerful as compared to the previous data structures like a list, because we are able to or maybe operations are able to be done or broadcast and done in parallel. So the same applies here. You can have a list and do some arithmetic operation with a number, for example. So these are not really compatible because one is a list or is a series and another one is just a single number, but you are adding them. So what will happen is the Pandas is going to interpret it in such a way as to say this 100 should be added to each and every element. So it will be more or less like taking the first element plus 100, second element plus 100, third element plus 100, and every element, if we have 1000 elements, every element you are adding 100 to it. So by just saying x plus 100, it means you've put something like x on position 0 plus 100, x on position 1 plus 100, on position 2 plus 100. So instead of doing that, you've just written something simple as this one. So we call it element-wise operation or broadcasting in Pandas. So if I run it, we see that each and every element now has been modified. We've added 100 to it. So that which is in position 4 now, the last one is 150 because we're adding 100 to each element. So it is applicable to all. We are broadcasting that operation to each and every element, and it's done element-wise. And there are so many other operations that will be done in that way, or that will be broadcast. Like in this case, we're just demonstrating to say sometimes if we have a list of elements like this one and we want to find the square roots of each and every one, instead of taking one element at a time, for example, instead, if we are to use the one above, instead of saying let me find the square root of that which is on position 0, and you find the square root. We have square root in NumPy, so here that's why we imported NumPy. Here is the first place we are using NumPy, and square root, so like this, and you do the same for that which is on position 1. Like this one, it is going to give us something like, oh, it's taking time, okay, something like this. And we can also do the same for that which is on position 1 and that which is on position 2. Instead, maybe position 2, instead of doing that, you can just run as if it's just a single number, as we've done here. So by doing this, it means the square root operation should be applicable to each and every element. So it's going to do that on 10, on 20, 30, 40, and 50. And the same here, if you want to have an exponent, it will be an exponent on each and every element. Or if even this one for the power, it means each element you are raising it to a power of 0.5. So 10 to the power of 0.5, 20 to the power of 0.5, 30 to the power of 0.5, anything that you can do. So an arithmetic operation, even like in this case, we've demonstrated how to use a plus, but even other operations like division, multiplications, they'll be applicable to each and every element that is there. So each element in this case has been square rooted, and in this case we are finding the what we call the exponent for each, and finally here we are getting the power of half, which is equivalent to square root. So the last output should be similar to the first output, because those two operations are actually doing the same. So that's how simple we can do. We can have that as a element-wise operations or broadcasting operations. Let's finalize the part of broadcasting or element-wise operations, and also finalizing the part of series by looking at this example. For example, if you want to know which which planets are closer to maybe Sun, something like that, we can have a list of what we call distances from the Sun for different planets, like here. So these are distances from the Sun for different planets. So these are planets, and we can create a series where the planets will be indices. So here planets will be indices, and this is our data. So that's our data. And if we are to run this one, let me comment out this, comment out this for now, and let me run this, which is the distance planets. If we are to run this one, what have we done? Okay, it's not distance. Our variable is not distance, it's just dist planets. Okay, so if we are to run dist planets, okay, if we are to run this one, we are getting something like that. So we've created a series like this one. So F 149 dot something from the Sun, this one, this one, this one, this one, C. So that's it. Then what we are doing in this example, we are interested in getting, here we have timeline, so we have divided it with this one. So what it means, by dividing by 18, that division will be applicable to all of them. So it's like 149.6 by 18, 1433 blah 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 by 18. Each number there is being divided by 18. So that's broadcasting, and we are keeping the result in here. So we've if maybe I can also just do something like this for now, and I say let me see what we have now under timeline and print it. Our numbers will be somehow different because the first number is here 149.6, but now after dividing it by 18 we have 8 point something. So we've applied it division by 18 to each and every element. And this statement under here, we are now just demonstrating something else. This we also did under NumPy, where we had what we call Boolean indices. So we are creating Boolean indices here. We are saying we want our index to be a list of, let's see what is happening before we go into details. So I'll comment this one as well. Just want you to understand what's happening. So we saw under NumPy that we're using something like this one to do the filtering. So let's try to print that one first. So I'll take off all these things. So we are printing this. What is happening here? We have this as output, and what will happen if we say that output is less than 40? So if we are to run it, this is the output we are having. On each and every element that is less than 40, it will be true, and elements that are above 40 will be false. So F, it means its value was less than 40, Venus was less than 40, and Mars was also less than 40. There are 3 planets whose distances, time distance or time light, were less than 40 in this case. So if you have something like that, which are less than 40, less than 40, less than 40, and you put it as the indices here, less than 40, less than 40, less than 40, less than 40, as indices, what will happen is that the corresponding values, like the value which was which in this case has got index of true, will be retained, and those with a corresponding value of false will be skipped. In other words, we are what we call filtering our data. So we are just interested in timeline data, but whose distances or whose values are less than 40. That's what we are doing there. So if we are to print what we have now after that, there are only 3 planets which had their values less than 40. So F, yes, 8 is less than 40, 6 is less than 40, and 12.1 whatever is also less than 40. So we are filtering our data here. If we wanted something that is beyond or greater than 40, then we should have the other 2, because those were above 40. So in simple terms, we are just doing a simple filtering here. We are doing a simple filtering. We are going to see this one again and again, and we saw that one in NumPy as well, how we can filter our data. So that's the introduction to Pandas, and that's how we use the Pandas to create a data structure called the series. Unless if there are issues with this one or questions, but otherwise I think with knowledge from Pandas, from NumPy, I think this should be a straightforward data structure. It's the equivalent of one-dimensional NumPy array. Only differences are the indices can be renamed or indices can be customized, and also it allows the storing of data of different data types, which is not possible in NumPy. Those are main differences. We can move to the most popular data structure that we're going to be using again and again, which is a data frame. A data frame is most popular because it resembles a spreadsheet like Excel, how we have our data in rows and columns. So a series, as we saw, is like just one column. It's data that has got only one column. But most of our data that we process are not made in that way or are not presented like that. They are composed of rows and columns like a spreadsheet, like Excel. So a data structure that is equivalent to that, or that is able to keep our data in that manner, is what we call a data frame. If we are to take it and maybe compare it with the NumPy, a data frame, you can consider it to be a 2D NumPy. So it's a 2D array where we have columns and rows, while a series is 1D array. So in most cases, as we're going to be seeing later, we create data frames by loading data from the file. If you remember in lab number 2 of our training course, we were able to use Pandas and we loaded data from the file. We are loading data, I think Adidas data, Adidas sales data from the file. That's a common way of creating a data frame. But you can also create a data frame manually. So there's a function equivalent to a function that we used to create a series. There's a function called a data frame that we can also use to create data frames. So before we look at how to do that, or how to read and create data frame from files, let's experiment some important operations of data frames by creating our own data frame. So to create a data frame, you need data, but you can also create an empty data frame and provide the data later. In this case, this is creating a data frame and we have given it a name of df, but that data frame is empty, has nothing in it. So it's just an empty container. And later we are saying, let's add the first data in it, and we are going to call it name. So it's like we are adding the first column. Let's add the first column, we are calling it name, and the data will be Bob, Sam, and Anna. So data going down under that column. And we are saying we can also add another column called grades and provide data. So this is how you add columns in a data frame. So we have two data frame. We have added the first one here, df, and specified the index, but our index is the named column, name. And here we are also providing something like that, and we are displaying what we've just created. Let's see what we have. So it's something beautiful. So this is the first column, this is the second column. So here we have two types of indices. We have indices for the rows and indices for the column. Remember, for the series, we only had one column and it had a name of 0. Of course, we will rename it to something else, but it had a name of 0. But here we have two indices for the columns, or headings for the columns, name and grades, and headings for the rows, which are starting from 0, 1, 2. But we can also rename them as we did with the series. If we wanted to add something else also to this one, maybe a third one, we would just do as before, as far as we provide 3 numbers or a list with 3 numbers. That would be added as the extra maybe column. Let's just demonstrate something small here. So we may want in the same to add another one, and we can say df, we want to add another column, and this column, maybe we just say what? Okay, maybe gender. Let me just say gender. So for each student, for the first one, the gender will be male. For the second one, second element, gender will be female. And for the last one, there are 3 items there. Gender will be male as well. Then I can display df again. So by doing that, it means I've added another column to these ones. Oh, okay, maybe Anne is male, I don't know. So that's how you can add columns. So if you have an empty one or even existing data structure called the data frame, you can add the other columns as demonstrated in this case. But another way of how you can create a data frame is to have a structure called a dictionary. So you can have a dictionary. So this is a dictionary, we have data, and our dictionary is starting from here, is ending from here. So this is the first element of a dictionary, and the dictionary has got 2 parts. Has got an what we call the index part and the value part. So for the first one, which is name, its data is a list, as we did there, and the other one here, its data is also a list. So if you wanted a third one, we would have a comma here and put the name of the field we want, colon, and the list that we want that column to be. But in this case, let's demonstrate with only 2 columns. So if we have something like that, then we can create a data frame by just passing this thing here. If you put data here, it means you want to create a data frame that has got columns, name, and grades, and on those columns, their data are what we have up there. So if we run it, it will give us something like this. We can also have a dictionary. It's still a dictionary, but instead of having just a list, we can have a Pandas series. So we can have a series. We are creating a series here. We are creating a series here. It will also work. So it's similar to what we did there, only that here we are now using Pandas series. There we just used a simple list. So whichever you are comfortable with. We are just trying to show you that even if you have with Pandas, you can convert it into a dictionary and use it to create a data frame. So it will still give us the same result. You can even have the arrays. So you can have a 1-dimensional array from NumPy, 1-dimensional array from NumPy, and use them to create a data frame. So the data structure called the dictionary can be composed of any of those things. It can be a list of NumPy array, maybe Pandas series, or a list. So if you run this one, the result will also be the same. Moreover, we can create a data frame even from a 2-dimensional NumPy array. So we can have a NumPy array, which is a 2-dimension. This is the first part. So this one is the first data items. Or in other words, you can think of them as the first row. So the first row has got Bob and the 76. So this data has got only 2 columns. So the first row will be this one, the second row will be this one, and the third row will be this one. We've not provided indices, so that's our data. And if we create this one, what we're going to have is this is the first row, this is the second row, this is the third row, first row, second row, third row. But we did not provide the names of the columns. So as with the maybe rows, the indices start from 0. So the same applies to columns. If there are no names, the columns start from 0. So we have 0, 1, 2, all the way. And the The same applies here, but we can rename them, or we can provide the names when we are creating our data frame. So it's the same as before, but we've just added the columns to rename them. You should remember that under series, we were able to use index to specify the indices. And we also use columns to specify the indices for the columns in a data frame. So if we do it like this, now we are going to create something similar, but now we are going to have headings for the columns. So we are just trying to show you different ways how you can create these things. But as I said, in most cases, we are going to be creating our data frame, from loading our data from the external data source, like a file. But we just need to understand what's happening in case we have a situation where we need to create our own data set. So as we did with the columns, that we can specify columns and rename them, when you are creating your data frame, you can also specify indices and rename them. So here, if I run it, it's similar to what we did somewhere before, but now we have even given the names for the indices. So we can have both columns and rows renamed or customized. So the first row, we have index standard 1, student 1, student 2, student 3, something like that. So here we're just now summarizing in case we have something that has been created and you want to change the indices. How do we change the indices when something is already created? We are specifying the indices when something was being created, but suppose we have this one created, which is our data frame def, and we have these indices and we want to change them maybe to something else. How do we do that? So here, first one, we are saying you can rename by using def.rename, and you specify whether you want to rename columns or you want to rename indices. So if you want to rename columns, then you specify that data as a dictionary here. So you are saying, I want this, the first one before colon, I want this name, code name, to be changed to first name. If you want to change all of them at once, then another one is grades. Then you can have comma here and say, and also I want grades, for example, then colon, to be changed to maybe grade, something like that. But in our case, we just want to change one. We don't want to change the second one. So we've just provided one item. And here we want this change to be in place and not out of place. So we have in place is equal to true. So it means modify the original one. It's going to modify our original data frame, which was created here with the name df. So and we are displaying it here down here. If I run it, we are going to see that the name column has been changed to first name. So here we are also saying we can also do it as follows. Instead of using df.rename, sometimes we can just say df.columns and specify the names, which are the new column names, and change the column that you want. Like in this case, the second column has been left intact, but the first one has been changed to first name. So if we write something like this, it means the first name, which was just a name in this case, would be changed to first name, but this one, because we are maintaining the name, it will not change anything, so it will be skipped. And if you wanted to do the changing out of place, then we were supposed to just write something like this without putting this part, which is equal to true, and that would create a copy of our name. So let me just try something there which is out of place so that I show you. But if we maintain the data, the name here, it means it will override each other. So let me try to put it def1, and I'm going to change grades to something like grade. So this is out of copy, it will create, out of place, it will create a copy, and we are displaying def1. So we are making changes. So yes, we have changed this one from grades to grade. But for sure, if I'm to write grade again, if I'm to display df, we find that df is not affected in any way. So we still have grades. So it was just a copy that was affected, but the original is still grades. So that's what in place or out of place actually do. So let me leave it as it was before. So that's how you can rename. So here we are showing you how to rename columns, but the same applies to how you can rename rows, the indices for the rows. Let's go down here and show how we can do that for the indices for the rows. So what about renaming the second row index? If you want just to change a single index, like this case, this one, we are saying, we can say df.rename and you say index and specify the dictionary as before. So we want it to change std2 to something like 2, and we want it to be in place. So if we do this, surely our index here has changed to 2. What about if we wanted to change all of them, not just one? Then we can do as we did before. We are using .column, but here now we are going to use .index and specify the new indices for the whole column. So that will change the whole column of indices. If we run it, then our indices now will be st1, 2, and 3, like this one. So that's how you can change columns, the headers, as well as the row headers, so to say, the indices for the rows and indices for the columns. Okay, so that's how you can create a data frame, and that's how you can actually rename columns for the data frame. Going forward, we now need to know how to insert data. We have a data frame, for example, it's an existing data frame. How can we add new data into that particular data frame? So think of this data frame that we have here, and we want to add some new data. So by inserting data, there are many ways. There are many ways we can think about it. We can think of it as adding another column, or we can think of it as adding another row. And we can also think of it as adding another column at the end or in between, or adding a row at the end or in between. So that's inserting. So how do we do that? So here we are saying, let's maybe insert a column. Let's start by inserting a column. We only have first name and grades, and we want to create another column called surname, and we want to insert it between what and what. So this column is on index number 0, and this column is on index number 1. So we want to insert. When we're saying we're using insert and specify the index position to say on index number 1, it means we want it to be here, and therefore grades will be more pushed to the right, will be on position number 2. That's what we are actually doing here. So we are saying, can we do the insertion? Can we do insert in that data frame on position 1, on index position 1? So we have index 0, first column, index 1, second column. Insert there. The name should be surname, and its data should be this one. So 1 is indicating the position to insert, and if we run it, it's going to take a position of 1, and the grades was on position 1, it has been pushed to the right. So that's how you can do the inserting of the row. But if you want to put it at the end, like in this case, you want to put it at the end, you just need to specify the new column name that you want, like that, and you have to specify the data, so equals data. So if you do something like that, then this will be inserted but at the end. So we are having this column created at the end. Okay, so let's look at how we can append a row in the data frame. So appending a row, how we can put it at the end. So we want to append a row. So if you look at this, we have 3, st1, 2, and 3, and we wanted to put another one down here. And what are we saying? To put something down there, of course, for rows, as is the case with the series, we use loc or iloc to specify the index of the row. For the indices of the columns, you just write the name of the column. But to avoid confusion with the rows, for the rows we use location. So we use loc or iloc. So if we want to insert something down here, we are saying, can we insert another row with a name or with index st4, and its data should be this one. So this one is going to be inserted on index which has got st4. If st4 was already there, then this data would override that data. But because we don't have st4 yet, then this is going to create a new record which will be st4. But if it was already there, it would overwrite it. So we have created our data like that. And sometimes you can have a situation from maybe, of course this will be common, maybe when you're working with your data, you may have data maybe that is coming from different branches. Let's assume maybe there are sales data for the mass, and we have 2 data sets or maybe 2 spreadsheets, one from a branch in Zuzu and another one from a branch in Blantyre, and maybe 3 of them and another one from branch in Lilongwe. And these data sets have got a similar structure. They are showing records for that math, but there's 3 separate data sets or 3 separate spreadsheets, Excel sheets. In most cases, when you want to do the analysis of such data, you may need to combine data from all those 3 places into one big spreadsheet. So you take all that data and stack them together, one after another, to create a big spreadsheet, which is a spreadsheet for the whole company. Then you can carry out the analysis on that one. So Pandas provide us with a way of how we can combine different data frames. You can load the data frame for the data in Blantyre, maybe in df1, and in Lilongwe in df2, and data in Zuzu in df3. Because this data has got similar structure, so to say, the number of columns are the same. What is different is just number of rows, because maybe one data or one data set can have many rows as compared to the other one, but the number of columns or the structure of columns should be the same. If the first column there is a product name, there should be also a column, first column in Zuzu, which is a product name, first column in Blantyre, which is a product name. So if it has got 5 columns, then each and every data should have 5 columns. So if we create data frames for all these, then we can use what we call concat to combine them into some big data frame and use that for our analysis. So that's what we are saying here. We are saying we can also concatenate or join our data sets. So if we can have another data set, remember we have a data frame that we've already created and we are calling it df, and so far we have 4 rows in it, and we are saying, can we try to create another data frame here? So the first column, you can see that we are using similar columns, so the structure of the data is the same: first name, surname, grades, and course, and we've provided those data items. And we can run this one. We have created it here, but with indices ST5, 6, and 7. We have created 3 of them, and indeed we have this data frame which has got similar structure. So we can think of this one as data from Zuzu, and the other one that we've been working with as the data from Lilongwe. So data from Lilongwe is in ST1, in just DF, and data from Zuzu we've kept it in DF2. And if we had another one from maybe Blantyre, we would keep it maybe in DF3. So after having these 3 data frames, we can use concat to join them and create something big for our analysis, because it would be very difficult to be analyzing data in parts, in bits. Maybe data in Zuzu analyzed separately, in Blantyre separately. But we create a bigger data frame, like in this case pd.concat, and specify the data frames that you are concatenating. In this case, it's a list of only 2. If we had 3, we would also put that one, comma, df maybe 3. If we had another one from maybe Blantyre, but in our case, it's just a list of 2 that we are concatenating. And if we run this one, it's going now to create something, or a data set which is bigger, and you can start your analysis on that data. So what I'm saying here is, in most cases, when you are having maybe multiple branches or something like that, you may have data that is common, have got similar structure, but in different files. So instead of combining them outside Pandas to create a very big data maybe file, like a Excel file, and load them here, you can just allow it to be loaded, and the Pandas would take care of them by joining them together into something big. So that's how you use it. Now we have a very big data set. As is the case with NumPy, NumPy had got attributes that we use to know maybe the size, the shape, and we also saw that with the series. Series also has got similar attributes, and the same applies to data frame. We may want to know the size, we may want to know the shape, we may want to know the dimension. So data frame, anyway, a data frame is like Excel sheet, so it has got 2 dimensions, rows and columns. So ND should give us 2 dimensions, rank of 2, and we can also be interested in index. Even under series, we had index and values. So the index will give you the indices, and the values will give you the values in that data frame, and the columns will give you the indices, but for the columns. So let's try to run this one and appreciate the output. So for the size is saying 28. So our data is saying there are 28 items, there are 28 cells. So if you count these ones, there are 1, 2, 3, 4, and 1, 2, 3, 4 up to 7. 7 times 4, all cells that are here are 28 indeed. And the shape is saying is 7 by 4. So 7 rows by 4 columns. And the rank is a 2-dimensional. So it's 2. The indices, df.index is showing you the list of indices. These are row indices. While df.columns, it will give you the list of columns. So these are headings for the columns. And the .value, it will give you now a list of values that are in our data set. So the values are given as a nested list, but each item is a row. So that's the second row, this is the third row, etc, etc, up to the last row. So that's how we can play around with our data using those attributes to know the shape, the column names, the row names, and other things for our data. With that, it can now take us to what we call updating values. There are two ways we may want to update our value. First one, maybe we may want to update a single value, but now we need to know, because this is like a table. For example, if we wanted to update this one, it means for us to refer to this, as is the case with the Excel. We have rows and columns. We use both. Maybe A1 to show that it's row number A and column number, maybe column number A and row number 1. But in here, we don't start with the columns, we start with the rows. So to say something about Pili, it means we have to say that one is on row ST2 and column surname. So there will be two indices that we can use to refer to a single cell. If we just use one index, like in this case, if we just say ST2, it means we are talking about the whole row. If we just use the index from above here, it means we are talking of the whole column. But for a single cell, we have to use both. So here we are saying, let's modify second row. So the second row is on index ST2 and the first column, which is the first name. So let's modify it to look. So if we run it, we are going to have that value modified, whichever was there. I don't know what was there. It was the sum. Sum has been changed to look here on index S2 and first name. But we can also update, for example, entire row or maybe entire column. If you want to update entire row, we can say, for example, a row with index ST4, can we update it? We just provide a new data set for that, and it will update whatever was there. So if the index is specified is already available in our data set, then it will just update the values. So our ST4 will now have Jag Chirwa instead of Mese Yakobe, and other values also have changed. And sometimes you may want to do that, but on a column. So you want to modify the column. It's not very common, of course, to modify columns, but you can modify rows. But maybe if a situation wants you to modify columns, so this is what you do. Def log, if it's the whole column that you are interested in, then you don't need to specify the row indices. So you can see we have just put colon. So we didn't specify the starting point of the row and the ending point of the row. We just put comma. So by putting just colon, it means every row. We want every row, but for the column called grades, can we have this data? So it's going to remove or update data which is available in grades, but for every row, because we did not specify the rows here. So if we do that, this should change. Let's see. So the last one here was 81, but now we've changed it to 60. Let's see. So that's what we are having. Our last student now has got 60. So we've updated the whole column for every row. You can also delete, as we did with the series. You can also delete. We use the same function called the drop, and the same thing that I said under series applies here. Drop is done in place or out of place. We've also seen some other actually operations above there that we're doing, maybe performing them in place and others were performing them out of place. So when we are dropping or we are deleting a data frame, we should know that a data frame is different from a series. It has got rows and columns. So when you want to drop, you may wish to specify, are you looking for a row, or do you want to drop a row, maybe a row, or do you want to drop a column? So if you are interested in dropping a row, then you need to specify exactly that for the rows, you specify the axis to be 0, and for the columns, you have to specify the axis to be 1. So by doing so, you are helping Pandas to say, okay, what you have given me, I should check them in the column or maybe in the rows. So if you're interested to drop columns, we use axis 1. For the rows, it's axis 0. So like in this case, we want to drop a column called surname, and we've said axis 1. So if I run this one, the surname is going to go. And if I wanted maybe 2 items to be dropped, then I am supposed to put that one in a list. Maybe I want items, surname to go, and grades also to go. Then I have to put it in a list, and axis is 1. So it's going to be looking for these indices, but now because I've said axis 1, it will be looking for columns that are matching this. But if it's just one thing that you are looking for, you may not need to put it in a list. You can just put its name here and you specify that. So this one is going to drop, and of course I've specified in place equals false because I don't want it to affect the original one. So it's not dropping the original one, but we can see that the surname is gone. And down here, if you want for the rows, you specify axis is equal to 0, and you can specify the indices that you want to be dropped. So in this case, we want ST5 and ST6 to go, and we are also having it out of place. So it will drop that. It's out of place, so ST5 and ST6 are gone. So that's how you can drop the rows. So it's the same one as before. We use drop. We just need to specify in this case now that we are dropping by column or dropping maybe rows. With all that information so far, we have to come to how to access values. We've of course already shown you in some way how to access them, but this section is just put separately to address issues of accessing elements in a data frame. So in a series, we are able to access elements, and we use indices, and the same applies to here. To access elements, you have to use indices, and if you want to access a row, the same applies that we're going to be using a loc, LOC for location, if you are using named indices in a row, or iloc, integer location, if you are to use the default indexing, which starts from 0. So here we are saying let's try to access first 3 items. So first 3 columns. Then because it's not just one thing you are accessing, if you are accessing more than one, you can put that as a list. But if it was just one, maybe you are just interested in surname, so it would just be something like this one, surname, and running it will give you only one column of surname. But if you are interested in multiple, so it's more or less also like slicing. You just want to take a portion from your data. So in this case, we are taking 3 columns. We are only interested in 3 columns: first name, surname, and grades, and put that as a list. And if we do that, we are going to have a portion of our data given to us, which will be first name, surname, and grades. And here we are saying, of course, you can achieve the same. What we did above, you can achieve the same by using numeric values like these ones, specifying the columns and rows. So if I take off this and switch on this one, what this one is saying is we want columns. Remember, the first part, the first indices before comma are for the rows and the last ones are for the columns. So we want those which are starting from 0 to 3, but 3 is not included, remember, when we are using indices. So it will be 0, index 0, index 1, and index 2. And here we have not specified the start and the end. So it means for the rows it should be everything. So we can run this one. It will be able to give us the same result. But sometimes we may want to say, but we just want maybe a row that is on the index number 2 to that which to index number 6. So index number 2, number 3, number 4. It will give us only that slice of data. So not every row, but just a portion of it. So we have limited the number of columns and the number of rows as well, using that syntax there. But if we don't specify anything here, we just put a colon, it means we are interested in everything. So that's how you can actually access your data using those indices. So with that information and the information we have from NumPy, we can use negative maybe indices, like in this case -3 if you want to get the last items. So maybe -3 column, colon, it means from index -3 all the way to the end. So this one will give us the bottom 3. So this one is going to help us get the bottom 3. And the bottom 3 is as good as using a head with some specification. Let's see. First of all, if we run this one, we are going to have bottom 3. That's bottom 3. But that is equivalent, if we are just looking for the bottom 3, is equivalent just to say df.head, bottom 3.tail, and you say 3. So it's equivalent to this. If we have something like this and run it, it also gives us the bottom 3. For the top 3, it will be head, or just something that should specify top 3 up here by putting, if we say df dot ilop, then we say colon 3. Then this one now is going to give you top 3. So that one is equivalent to head 3. So there are many ways you can access your items. So it's equivalent to head 3. Okay. And here we are also trying to show you that sometimes you can even specify the named indices to say I want to access the index ST5, ST6, and ST7. So it's up to you. You can use that. It also gives you the rows on those particular indices. So let's leave it to bottom 3 as before. So to get a specific value, you need to specify both the row, column, and the row index and column index. Like in this case, we are saying that which is on row number, index number 1. So indices start from 0. So this is index number 1. So this is the second row. And the column number 0, which is the first column. So if we run this one, it will give us a single value that is available on a second row, and first column, which is local. But if you want a slice bigger than that, you can specify something like this. I think we already did that. You can specify the start and end, and also start and end here, so it will slice any part of it. You can also do the same using the named indices. So you say, I want from ST2 all the way up to ST4. So ST2, ST3, ST4, those are 3 records. And I want columns, first name all the way up to surname. So first name and surname will also be shown. Something like that. So that's part of also slicing. And yeah, so that far I don't know if there's any question, comments, anything before we finalize Pandas data frame by looking at Boolean indices. We saw something like this one also, and of course the series. Any comments, questions this far? So the indices can also be a list of Boolean values. Here we are saying we can specify the indices of the data frames as an array of Boolean values. It's very important. And if we have as an array of Boolean values, only those values that are true will be picked. In other words, we use this one to filter our data. We use the Boolean indices to filter our data, and we did that under NumPy. We also did that under series, and we're also just repeating them here because this is something that we're going to be using again and again to filter your data given in a data frame. So in our data frame that we have above, we want to filter the records that have got grades greater than 80. So we want to filter this data. We want to get only those that have grades, have got this column greater than 80. So how do we achieve that? We use what we call Boolean indices. So this that is inside, I can take it out for now. I can copy it out, and maybe I can first of all put it here as a separate one. If we just write something like this one is going to look into the column of grades and look if that one is greater than 80. And if I run something like this, this is what I am getting. Why is it taking time to give me that? Okay, so this is what I am getting. In that column, it's saying the first one is not greater than 80, the second one is greater, the third one is not. So there are 3 that are greater than 80, ST1, ST5, and ST6. They are greater than 80. So this will be a list of indices. It's a list that we are feeding here. So in other words, it's like the whole of this part will be replaced by true, false, whatever. It will be replaced by this one. So only rows that match true will be retained, and those rows that match false will be discarded. So that's what is happening in here. So we just write it together like that, but you can choose to separate them to have the indices written maybe above here to say these are indices, and you can put it here, and you can feed in the indices here. It's also all up to you to show that the indices are created here, and here we're just providing the indices. So if you do this, they should give us 3 because we had only 3 truths up there. So these are grades that are indeed greater than 80. But sometimes you may want to have maybe 2 or more conditions. Like here we are saying not only those which are greater than 80, but we want them to be greater than 80, and also they should belong to programming. So we are now using, we are applying conditions on two columns. We want those whose grades are greater than 80, but their courses are programming. So this is doing that. This is first part, which is going to do greater than 80, and this is the second part, which is going to check columns that are programming. Then we are going to do the ANDing. It is going to check the rows which have got true on left hand side and true on the right hand side. They are greater than 80 and they are also programming. So from our data, we can see that greater than 80 already gave us this, and the programming that are greater than 80 is only one. So if I'm to run this one, it will only filter my data and give me only one record that match both criteria. It's greater than 80 and it's also programming. So these are things that we commonly use to filter our data. We are going to have them again and again for filtering our data. Another important aspect or function that we are going to be using again and again, this one, let me change to something like this, is how to use group by. So the group by tries to group our data. It's going to be very important for summarizing our data, because when we have our data, we may want to summarize our data on maybe a certain column. Like in this case, we may want to summarize our data, for example, on courses. We want to summarize them. Maybe we want to count how many students were taking programming. Let's have the bigger one. We want, where is the bigger one? Oh, the bigger one is very far. Okay, here. So we want to count how many students were taking programming, how many students are taking maths and English. We want that particular summary, maybe just counting. It can be anything, but we can do it for counting. So to do that, you need to, where are we? You need to use a group by. So here we are showing you group by. We are saying on our data frame, we can use group by, and we say we want to group by the course. So you specify them here. If you are grouping by a multiple values, you can put it in a list, but here it's a list of only one item, so it's as good as not putting it in a list. So whether you have it as not a list like that, it will still work because it's just one, or you can have it as a list because that's too general, that even if you have multiple fields that you want to use for grouping, you'll still be able to have that one, and you can just include the other fields. But in this case, we have only one field. So you are saying we want to group by courses. In other words, we want our courses, whether it's counting, we want to count by courses. So we are going to group by courses, and of course we need to specify also another column that you want to base your grouping. So we've just picked any column. It can be any column in this case because our main interest is on counting courses. So we can just give it any column. So we've picked a column of grades, and here we are specifying that let's count. So if we do that, let me take off the last part. If we do that, this is what we are going to have. So these are courses, but these are grades. So we are saying English, there are 2, maths, there are 2, and the programming, there are 2. But grades is not very descriptive in our case. So we need something better. Something better that can be here. Not really grades, it's descriptive, but it needs a field. So we cannot just type something here like this to remove that part. So it will need a proper field that should match what we have in our data set. So a better simple way is just to rename. After we've done that, up to here is giving us this. So this one is like a series. Then we can say, but we don't want the output to show grades because we are not really interested in grades. They are just numbers, counts. We just want to know English, how many students, maths, how many students, and programming, how many students. So we can rename it and give it any name. So I want it to be maybe counts, or I can try to have it as a number of students, something like this. So if I run it, that one will be renamed. So this is more descriptive. So these ones are our courses and these are number of students. So that's how you can use a group by. We are going to be using group by, I think, again and again in lab number 5 that I've given you. You also meet group by for the data that you are going to do analysis on. So that's a group by. The last part of our data frame will be on a simple data cleaning. The concepts that we've covered so far are enough to help us comfortably work with the data frame, but we are remaining with the important parts, which are cleaning, because when we have our data, above there, the data that we are working with, we are creating them ourselves, but the data that we can load, maybe from Excel file or something else, may have some issues. So issues of cleaning that data is very important. So here we are just demonstrating with something simple. We are creating a data frame, but this data frame has got incomplete data. It has got some fields that are, or some cells, that are missing. So don't worry about the details of how this one is being created. It's just a sample data. In our case, most of the data will be coming from the files. We'll not be creating them ourselves. But let me just run this cell and take you to our data set. And we are saying this data set has got missing values. Like a second row here, we have a missing value. So in Pandas, a missing value is represented as NaN, standing for not a number. So there's no value, there's no value here, there's no value here, there's no value here. So they are missing values. So as a data analyst, one step, or the first step you do after loading your data, is to clean your data. You look for incompleteness of your data and make a decision how you are going to handle with such incomplete records. There are many ways you can do about it, or many decisions you can do. You can choose maybe to delete any record that has got incomplete data, if that is okay with your goal or something that you want to use your data for. Sometimes you may want to not delete those records, but maybe fill those missing data with some values. Sometimes you may want to fill them with zeros, so you don't delete those data records, so you can just put some zeros. Sometimes you may want to fill in maybe using an average. So if we are here, for this one, we can calculate average for the whole column and fill this one with that average and this one with that average, and many other methods that are there for filling our data. But the simplest one, if the data is big enough and there are just some few records with the missing data, you can just delete them for better analysis. But all in all, before you do any analysis, make sure you have dealt with the narrow values. You have dealt with missing data. So you have to clean them, you have to remove them, or you have to refill them before proceeding with your analysis. So after loading your data, the next thing to do is to start cleaning. But first of all, you have loaded your data. Your data can be very big. This one is a small data set. We are able to see that there are missing values, but your data set can have millions of records, maybe thousands of records. How do we identify the missing values? There are many ways. One way is to use the info. So the info method on our data structure, and our data frame is called df score, the one that we created above there. So if we say info, the info is going to give you so much information, and part of that information will help you to know if you have missing data. So it is saying there are 8 entries in our data. There are 8 of them. And if you go up here, this is our data, 8 of them, from index 0 up to index 7. Index 0 up to index 7. And the first column of name has got 8, and it's of data type string object. So it means this column is complete. The second column, the second row, has 6. So this column is having missing data, and the other 2 also are having missing data. They are not matching with the 8 entries there. So that's one way of how you can identify if they are missing data. Another way is to use count. You can use count to do that. But before we go to count, sometimes you can just use isNull. isNull will count how many null values are there for each row. So it's saying isNull, and we have put sum to count. So isNull is going to help us sum up all of them. So for the name, there's only 0, score 1, there are 2, score 2, 1, score 3, 1. So from here we are able to see that indeed they are missing data. If you just want one value, one single value, then we can repeat the sum. We can use it to sum.sum. And this one is going to sum everything and just give us to say in this data set there are 4 missing values. Sometimes you can use count. So the count will also give data for each column, and we can see that these values are not matching. It means some of them have got missing values. So this one is complete, it has got 8, this one 6, 7, 7. So they are missing 2, they are missing 1 here, missing 1 here. So you can use those to check the data if it's complete or not. Now that we have noted that our data is not complete, what we must do is to see how to eliminate them. So we can eliminate them using drop nar. That's the simplest way. You just come there and drop everything. So here we are showing you to say you can use drop nar and specify which axis you want to drop. You can drop the whole column that has got missing value, but mostly we don't drop the columns. We drop the records, the rows. So we drop axis 0. Rarely, very rarely, we'll be dropping columns, but axis 0. Unless if that column is not very important in our analysis, then we can drop column. But in this case, we just want to drop axis 0. So every record, and it's implicit, in place false, so it is not going to affect the original one. So if we run this one, we can see that it is now only giving us records that have got complete data, and we can now carry out our analysis on this data because it's now complete. Another way is to just specify how you want to actually fill your data. So you can specify how you want to fill your data. Okay, so this one you can disregard this one. This we are just trying to see the averages, but we are not doing anything there. So you can discard that, but this is what is supposed to be presented. So how you want to fill that data. So you can fill that data. You can say we just want to use 0 wherever there is no value. So use fill now. And if I do this, fill now with 0, everywhere we had null, now we have zeros. So that's one way you can clean your data. Another way, you say, can you fill a forward fill? You can use the forward fill, which is the F fill, or you can use the backward fill, which is the B fill. Let's see F fill, what it does. Let's see, first of all, like John, I think this one has got has no value. So let's see what will happen there with F fill. If we have F fill, because that's a forward fill, it takes the value before it and fill the missing value with that. So there was a missing value here, so it will just copy that one here. So the same, I think, should apply here. It means maybe this one had a missing value. So we can see that we have places with the similar values. So that's what F fill does. While the backward fill, the same, but backward fill, let's try the backward fill. Let's check off this one. So the backward fill, this one, previously we copied this one, but the backward, it will take a value before it and copy it to this one. So that's a backward fill. So it has taken a value before it and copied it back to that one. So those are methods that you can use, but for the most of the cases, dropping the records with the null values is a common way to do it. But of course, there will be some other data sets where you have to make a decision of filling in the gaps, not necessarily deleting the records. So these are just some of the methods. And the last method that you can use to do that is to use interpolating. So you can interpolate your data, not necessarily just to take a previous value or the next value, but you may want to interpolate it maybe linearly or using some other methods. So without going into details, but here we have just an example of how you can do that. You can interpolate to say by rows or by column. So here we have just shown you how you can do that by row. So it will do the interpolation by the row, and we are using a linear method to do that. So this is a structure, but interpolation only works on numeric values. If you have other numeric values, then you may wish to exclude them. So the code below is trying to show you how you can specify the fields where you want interpolation to take place. Like here we just want that to be applicable on score 1, score 2, and score 3, and we can do that using this code. And after that, we are specifying the interpolation method at the end here. So this is going to actually using linear method. If we run this one and just see, appreciate the output down here, we see that this value, it has not just copied this to here, because here it was the missing value, and it has not just copied this one to here as well, but it has it used the data set and tried to come up with the most probable value that would nicely fit into our data. So it's not necessarily just copying another data, but coming up with data that you think if we are on a linear or a line, a straight line, that value would be very close to all other values that are making that particular straight line. So these are just some other methods, but as I said, the most commonly used one would be maybe just using drop now, which will drop the records for you. Okay, so I think we can be wrapping up here, but lastly, I'm just trying to show you something small here to say you can create another column from existing columns. Like in this case, we have a column of score 1, we are adding with score 2, we are adding with score 3, and we want that the result of those ones to be column called total. So if we are to run this one, our data set is going to grow, and we are going to have this one. Of course, we are having data these ones because I did not fill these values. That's why I still have some other issues here, because I did not fill them in place. But I was just trying to demonstrate that we can have this column added. By just adding the values, we are able to create another column, as simple as that, using such a statement. Getting values from various data sources, especially maybe loading our data from CSV into a data frame. Unfortunately, with time, we'll not be able to demonstrate that, but that's something that we're going to be doing in lab number 5. So without going into this lab number 5, but I just want to highlight things that I've given you lab number 5 and data for lab number 5. I've also given you all the code for doing part of this analysis. In that lab number 5, we are trying to answer these questions. Are there any missing values? How many properties are there per region? What are the average property prices per region in US dollars? And the other things. So I would like you to go through this lab using the knowledge presented in lab number 4. I want you to see if you can appreciate how that knowledge is being used in this lab to do analysis. And of course, at some points, there are also some visualization. But visualization have not been explained here, because visualization will be explained in our next class next week. As our last week, we are going to finalize by looking at the charts. But the knowledge we have should be enough to understand or to answer some of the questions that we can have on the data that I've given you here, which is data from Brazil about real estate. Sorry for taking you up to 6 minutes past 8, but we can stop here for today, unless if you have some questions that you'd want me to address. Otherwise, I thank you for attending this session. Thank you.